This video presents a demonstration of a toolchain for designing and deploying energy-optimized sensor-based adaptive software on heterogeneous platforms. This demonstration was built in the Cerbero H 2020 European project, and results from a collaboration between INSA-REN, UNIS, and UPM. A sensor-based adaptive cyber-physical system consists of three main components: a physical environment, an adaptive software, and a heterogeneous platform. The system interacts with its environment through a set of sensors that capture physical properties of this environment. Typical properties measured by such sensors include time, temperature, sound, motion, light, and user interface. All of these sensors generate data that is fed to the adaptive software part of the system. The software part of the system specifies the computations that must be executed to process the data received from the sensor. As a result of these computations, the software part will interact with its environment, by activating actuators, or by providing valuable information to its users. The distinctive feature of adaptive software is that the nature and the amount of computation is changing during the execution time, adapting itself automatically to changing environmental conditions. In each configuration, the adaptive software performs computations requiring different computational workload, and exhibiting a different degree of achievable parallelism. The number of reachable configurations of such system may be very large, or even infinite, as it depends on the countless and unpredictable physical phenomena measured by the sensors. Consequently, since it is impossible to predict or optimize all configurations at design time, the only solution is to let the system perform self-optimization when a new configuration is triggered at runtime. The heterogeneous platform is the hardware computing system on which the adaptive software is executed. Modern heterogeneous platforms not only consists of multiple core processing units, but also embed application-specific accelerators, reconfigurable logic, hierarchical memory systems, peripherals, and on-chip networks of communication. The key challenge that must be addressed when building such an adaptive system is to use efficiently the resources of the heterogeneous platform. Indeed, inefficient management of available resources leads to a poor latency and throughput of the system, and results in a large energy consumption. This optimization objective is particularly challenging since optimizations and resource allocations must be performed on the fly at each reconfiguration of the system. The following demonstration presents a toolchain providing both design and runtime support for adaptive software system. The sensors used in this demonstrations are a USB camera and a timer embedded on the heterogeneous platform. In this demonstration, the camera is both the sensor providing data to the software, and the sensor triggering the reconfigurations of the adaptive software. The adaptive software implemented in this demonstration is an image processing algorithm used in many computer vision applications. The input image received from the USB camera, at a rate of 2.4 images per second, is first split into its luminance component Y, and its two chrominance components U and V. In order to evaluate the amount of information contained in each color component, the algorithm computes the standard deviation of each component and compares it to a threshold. The result of this comparison is used to activate image filtering computation only for components containing enough information, like the luminance component in our example. The output image of the algorithm is obtained by merging the filtered component. Since the variance of each color component is reevaluated for each input frame, reconfigurations may occur and the filtering of color components may be activated or deactivated dynamically, thus conferring its sensor-triggered adaptive behavior to the software. The adaptive software of this demonstration has been designed using the Preesm rapid prototyping framework from INSA-REN. The PySDF model, which is a short name for the Parameterized and Interfaced Synchronous Dataflow Model of Computation, is used for the specification of application in the Preesm framework. As shown in this graph, which specifies the adaptive software of our demonstration, a PySDF graph consists of computational blocks called actors, and represented by the gray rectangles, that exchange data on a set of first-in first-out queues, represented by gray arrows. A set of parameters, represented by blue pentagons in the upper part of the graph, influence the behavior of the actors. The internal behavior of actors is described using a programming language, except for the blocks highlighted in red, which are hierarchical actors whose internal behaviors are described with another PySDF graph. Specification of reconfiguration behavior in the PySDF model is supported by allowing an actor to change the value of a graph parameter during the execution of the application. For example, the parameter highlighted in red, whose value is set by the make decision actor, is the one responsible for activating and deactivating the filtering of a color component. The PySDF model of computation provides all the necessary semantics to specify parallel, reconfigurable, and portable adaptive applications. The heterogeneous platform used in our demonstration is an Odroid XU3 board embedding a Samsung Exynos 5 chip. The Odroid platform embeds an ARM Big Little architecture with 4 big A15 cores, and 4 small A7 cores. The platform also embeds 2 GB of memory, input-output drivers, an energy monitor, and a graphical processing unit that is not used in this demonstration. The deployment of the adaptive software on the heterogeneous platform requires the use of a runtime manager that allocates the resources needed to run the application. The Spider Runtime Manager, developed at INSA, in collaboration with UPM and UNIS, is dedicated to the deployment of PySDF applications on heterogeneous platforms. Spider adopts a master-slave organization where the master processing element is responsible for mapping and scheduling actor executions on available cores, including itself. The master core is also responsible for managing the reconfiguration of the PySDF graph, using the dynamic parameter values provided by dataflow actors. Finally, the Spider runtime continuously monitors the execution of the application to better optimize its deployment, and to ease its debugging. The overview of the components of our adaptive software demonstration is now complete. In this video, we can see the complete setup of the demonstration. On the left, the laptop is running the Preesm framework used by the application designer. The code generated by Preesm is sent to the Odroid board, on the right, through an Ethernet connection. The Odroid board is connected to a USB camera feeding data to the adaptive software, and to a computer monitor for displaying the application output. We are now seeing the laptop screen with the Preesm framework, which is a set of Eclipse plugins. In the opened PySDF graphical editor, it is possible to edit the graph and its properties, to navigate the graph hierarchy, and to see what function is associated to actors. The Preesm framework also contains an editor for high-level architecture models. Here, we can see the architecture model of the Odroid platform, which contains 4 A15 cores and 4 A7 cores, all communicating through a shared memory. The last input of the Preesm framework is a scenario which defines deployment constraints for a specified pair of a PySDF graph, and an architecture. For example, the scenario defines the mapping constraints to allow or to forbid the execution of actors on specific cores of the architecture. The scenario also defines the execution time of actors of the graph, for each type of core contained in the architecture. In this example, we can see that the Sobel actor requires 150 time units on A7 cores, and 100 time units on A15 cores. Using the PySDF graph, the architecture model, and the scenario, the Preesm framework generates code for the Odroid platform. We are now seeing the output image generated by the adaptive software. On the top left corner, the number of frames processed per second, the power consumption of the A15 and A7 cores, and the energy consumed for the processing of each frame are displayed. At the moment, only the Y component of the input image is being processed. Giving a look at the Gantt diagram generated by Spider, we can see that the read and display actors are the most time-consuming actors, and are both executed on an A15 core. Most other image processing actors are executed in parallel to these two actors, thanks to the pipelining of the application. Since the degree of parallelism of the processing of each component is 4, A15 cores are mainly used for image processing as they are faster and available. The energy consumption in this configuration is on average 1.92 joules per frame. When new color appear in the frames captured by the camera, the processing of both the U and V components is enabled. As we can see in the corresponding Gantt diagram, the additional computation needed to process the two chrominance component, which each have a resolution 4 times smaller than the luminance component Y, are mapped on the A7 cores. Indeed, although these cores are slower, using them is a smart decision, since all the A15 cores are already used by the read and display actors and for processing the luminance component. In this configuration, the average energy consumption increases to 2.35 joules per frame, due to the additional processing performed on the A7 cores. When only the Y and V components remain, the energy consumption decreases to an average of 2.15 joules per frame. To better appreciate the energetic performance obtained with the Spider runtime, we now compare side by side two implementations of the adaptive software. On the left, no information on the platform heterogeneity was given to the runtime manager, which thus sees 8 identical cores in the architecture. On the right, the runtime manager is aware of the platform heterogeneity, thanks to the information filled in the Preesm scenario. For all configuration, the runtime manager on the left consumes more energy per frames than the runtime taking heterogeneity information into account. A cause of this difference in energy consumption is that the runtime on the left is unable to keep up with the frame rate of information given by the camera, because of poor mapping and scheduling decisions. This low processing throughput leads to longer processing time per frame, which in turn leads to higher energy footprint. Thank you for watching this video. The Preesm framework, the Spider runtime manager, and the adaptive software presented in this video are open source projects available on GitHub. Tutorials for both tools, and further documentations are also available on preesm.org.